All right, so today we're going to finish the USHAG and K part. So last time we did the first half of this reaction, where we did the reactants part, and we started talking about the products. Okay, so we considered a two-level system, or a system of having three levels, each spaced by 200 wave numbers, and singly degenerate. So we calculated U, which is the internal energy, S, which is entropy, H, which is enthalpy, A, which is the Helmholtz energy, and we talked a little bit about that being a constant volume situation, which is useful in energy when they have stainless steel vessels where they have a fixed volume and pressure fluctuates, and then delta G, which we use in academia mostly because our systems are open to the atmosphere, so we have constant pressure, and so that's why we are more familiar with delta G. Then we said, let's say this system is in contact with the products where we have a doubly degenerate and triply degenerate level, but the same energy level spacing. And so here's our reactants. These are the numbers that we had from the reactants. Roughly 88 wave numbers of energy. Also commented how that's the average energy of the system. So notice there is no energy level at 88 wave numbers, but that's the average energy of the system because we have a few molecules with 200 wave numbers of energy, very few of 400, and a whole bunch at the ground state. So that's the typical Boltzmann concentration or Boltzmann population statistics, that the lowest energy level is the most populated if they're all the same degeneracy, okay? And then if as you go up, they get less and less probable to be populated. You can have more molecules in an excited state if you have more chairs there. It's like musical chairs. If you have a degeneracy in the second and third and fourth energy level, then there can be more molecules in, say, the third or fourth excited state if you have degeneracy. So then we have also the enthalpy for the reactant, the Helmholtz energy for the reactant, and the Gibbs energy for the reactant. Now, none of these numbers, like you see a negative sign here, none of these numbers have anything to do with spontaneity. So don't be thinking about positive or negative numbers yet. That's when you get to the deltas. Okay, so when we get to delta A and delta G, those two things will determine whether it's spontaneous or not. So let's calculate for the product partition function. So I like to do these in tables. We have the index number 0, 1, and 2. You can consider those quantum numbers. We have zero wave numbers of energy for the ground state, 100. Oh, it should be 200 and 400. Oh, look at that. So this is a copy-paste error. I calculated with 200 and 400. Okay. And then the degeneracy 1, 2, and 3 going up. And so these are the Boltzmann factors. So for the ground state, we have e to the minus 0. For this one, we have 2. That's the degeneracy times e to the minus 200 over kt. And the kt at room temperature was 200 wave numbers. Okay, so that's e to the minus 1 times 2, which gives us the 0.761. Okay, so that's this number right there. And then the 0.35 is 3 times e to the minus 2. That's 400 over 200. So that's this Boltzmann factor. So we add up all of those Boltzmann factors and we get the partition function of 2.196. Are you with us so far? It's pretty much, you could do that given this question. Yeah, exactly. Okay, good. Then how do we calculate the probabilities? Yeah, it's that particular Boltzmann factor divided by the partition function. So if we take this 0.435 and divide by the partition function, so this one divided by Q is equal to the probability here, 20%. And the 0.761 divided by Q is 35. And this one should be close to 50%, right? 1 over 2. So let's see what that is. Divided by Q equals 46%. So that checks out. It's always good to add these up, see if they get to 100. So 6 and 5 is 11. Carry the 1, 4, 5, 6, 7, 8, 9, 10. Yeah, so we end up with 101. So there's a rounding thing there somewhere, but that's close. That's what we expect. Okay. Now, how much energy does each of those states deliver to the whole, like the average? So we have 20% at 400 wave numbers. So this one times 400 equals 79 wave numbers for that. This one times 200 gives us 69%, or 69 wave numbers. And then 46% times 0, that one's easy to do, equals 0. So we sum those and we get 148 wave numbers of energy. So that's our average energy on the right. So this one had 88, so it was like less than halfway across this right here. So we had 88 wave numbers, and this one is 148. Yet they're at the same temperature. And I just try to get you guys to puzzle over that, because that does seem strange, doesn't it? They're at the same temperature, but the one on the right has more energy because of those statistical chairs, the degeneracy. There are more molecules in the excited state, so the average energy for the products is higher. Okay. So U is going up. Okay. So it makes sense. I mean, we sort of think about things going downhill in energy, right? And so it seems like the reactants should be favored in this situation, doesn't it? I mean, logically, that's what it seems. Okay. We'll see where that goes, okay? So we can't make that decision with internal energy. Internal energy, if we go to the products, internal energy goes up, okay? But let's see what all the other numbers tell us. We have to calculate enthalpy. We have to calculate entropy. We have to combine the enthalpy and entropy together to get the Gibbs energy. Gibbs energy is what tells us whether something's moving forward or backwards. Okay, so not internal energy. Any questions on this? I'm going slow because I want to make sure you guys don't just nod and then get to the test and not do it right. Right? We've done 3 or 4 of these, so it's okay if you get it. Let yourself get it. Okay. All right, so let's go to the product thermodynamic values. Here's all of our USHAG equations down here. So this most definitely needs to be on your note card. Right, you need to be able to do any one of those calculations. I probably won't make you do the whole thing because you're going to run out of time. But you need to be able to drop into this procedure at any point. Okay, so you need to be familiar with the whole thing, and then if I say, all right, you've got entropy and enthalpy, what can you calculate with that? And go ahead and calculate it, and then answer these questions. Okay, so here's the entropy, the products. We have the internal energy here, U over T, and then this equation says R ln K, or R ln Q, okay? And in this case, R needs to match the units that we use here. So if we're using wave numbers here, we need to use that Boltzmann factor in wave numbers per Kelvin. Okay, so we use the 0.695. If this were joules per mole, then we would use the gas constant R of 8.314 joules per mole Kelvin. And then the natural log of the partition function, Q. All right, so we end up with 1.045 wave numbers per Kelvin for our entropy. Now looking back a couple of pages, the entropy's gone up. So let's go back a few pages. Let's look at our entropy here. Oops, right there. Entropy was 0.5 wave numbers per Kelvin. And look, we have now On the left, we only had 3 energy levels. On the right, we have 6. So entropy is a measure of the options a molecule has. We talk about it being a tendency towards disorder. You've heard that. Entropy is a tendency towards disorder. But I think you guys now are ready for a more precise definition. Okay, entropy is options. Okay, so disorder means options if you think about it, right? But entropy is having more options. There are more options in the products than there are in a reactant, so the products have a higher entropy. Okay. It's directly related to that partition function, right? It's the natural log of the partition function. So if the partition function goes up, the entropy goes up. And what does the partition function tell us? This is something I've been trying to beat into your heads. The partition function is an estimate of how many energy levels are populated. So if I populate more energy levels, I have more options. So that's what we mean by entropy being tied to more options. If I came into this room and somebody had cleaned it and taken all the chairs out and they had only put one chair back, it'd be really low entropy. I could only have one chair that I could sit in. But if they bring in all 22 chairs, now I have 22 possibilities. I have a lot more options and a lot higher entropy. Okay. And so in this case, the products have 6 chairs and the reactants only have 3. So naturally the products in this case, at the same temperature, the products are going to have higher entropy. So let's calculate the enthalpy. So this is U plus RT. So again, U is in wave numbers, so R, we need to use wave numbers per Kelvin. So we get 356 wave numbers for enthalpy. Now, enthalpy is the heat of reaction, so that's how much heat the products have. We'll have heat that the reactants have, and we'll be able to tell whether this was endothermic or exothermic. Did it take in heat or did it give out heat? So we use H for enthalpy because H indicates heat. So we're going to be thinking about heat when we see enthalpy. Now let's do the Helmholtz energy. So it's U minus TS. And so we have, here's U, 148, temperature, and then S, that entropy comes down, and we have the minus 163. So that's the Helmholtz energy for the products. And then the Gibbs energy for the products. It's H, so we bring the enthalpy down. So you see how this builds. Once we have U here, then it goes into the H calculation, and the temperature is there. And then once we have the enthalpy, it goes into the Gibbs energy. And in this case, S comes down and is used there. So it all builds on itself. So that's our Gibbs energy, 44 wave numbers. We can't really tell the A and the G are useful for spontaneity, but we can't do anything with these because these are sort of the absolute magnitude values of A and G. They're not deltas yet. But we have A and G for our products and A and G for our reactants. Let's take products minus reactants and get all of the deltas. So this page is going to have all of the deltas on it. So delta U for reaction is the U product minus U reactant. So 148 minus 88, so we have a positive 60 wave numbers. So the internal energy went up. Oh, another mistake in my crazy notes. I'm sorry about this. So let me go back over here. I gotta change that because it's too ugly. Okay, so bear with me 1 second. Grab this guy. Delete this one. Pardon? Did it work? Yeah, okay, it changed. Good. All right, good. Little quick change. Okay, so our energy went up. So in terms of internal energy, we don't have it's endo. We don't have a thermal is heat. So we'll see what the enthalpy does. We don't have an endo-exo thing for the internal energy. Like there's not a word that we use. For the entropy, okay, we also don't really have an endo-exo thing for the entropy, but entropy did go up. So products minus reactants, the entropy increased by 0.45 wave numbers per Kelvin. Then we get to the heat of reaction, and this is endothermic. Okay, so we can see that 60 wave numbers, it's positive, it's greater than 0. So I'll go ahead and write that in. Delta H is greater than 0. And then here's the Helmholtz energy. It's negative. So this is, when we take into account the increase in entropy, this reaction is spontaneous in the forward direction. So this is delta A is less than 0. Therefore, do y'all know the 3 dots for therefore? Therefore, spontaneous. And then we have delta G, 44 minus 120, also 76 wave numbers. Less than 0, therefore spontaneous. And then we calculate the equilibrium constant, which we'll get to how this is, we'll sort of derive this equation in a minute, but we have the delta G over RT, and then it's e to the minus that value. Again, if our delta G is in wave numbers, then we definitely want to use the wave numbers per Kelvin version of Planck's constant so that all the units work out. And this is 1.44. So K is greater than 1. Therefore, spontaneous. So there's 3 ways to know if, as the reaction is written, if it's spontaneous in the forward direction. If K is greater than 1, then our products over reactants, there's more products than reactants, right? So it's spontaneous in the forward direction. Delta G and delta A are negative, so that means that it's what we call exergonic. So let's look at these phrases. Now, and we could also do the K calculation using the partition function over the reactant partition function. And that's always satisfying when you have 2 equations or 2 ways to calculate the same thing. You might catch an error if you can check your work that way. So yeah, the product's partition function was 2.196 and the reactants was 1.526. So we call this positive delta H, we call that endothermic because the heat is going into the reaction. In order to get that enthalpy to go uphill and the internal energy to go uphill, it takes in heat from the surroundings. So it's endothermic to get these molecules to go to the products. But it is spontaneous. So why is it spontaneous? It's the entropy that's driving that. So since there are more options on the product side than the reactant side, if we throw molecules at this system and they populate all of the energy levels statistically, and then we look and say, well, wait, let's divide this. I've got my products here and my reactants here. How many products do I have? Well, I've got 2.96. And how many reactants? 1.5. I've got more molecules in the product's energy levels than I have in the reactant energy levels. So that's a totally statistical view of reaction chemistry. So molecules come into this energy level and they have all of those options. They can go on the reactant side, they can go on the product side, they don't care. And they switch back and forth. That's what equilibrium is. There's the forward rate and reverse rate are at equal rates at equilibrium. And they all populate those energy levels based upon the temperature that they have. And we end up with this statistical driving of an endothermic reaction. And we see that almost, well, as far as I can tell, well, no, this tells us it has to be. Endothermic reactions are going to have a higher entropy. Entropy is the only thing that's going to drive them to be spontaneous. If we look at the other form, like you could write this as delta G is equal to delta H minus T delta S. You could calculate it that way. And you see it's this competition between the change in entropy and the change in enthalpy. So if this number is positive, meaning it's endothermic, we have to have a larger positive delta S. And it's temperature dependent, right? So I could raise the temperature, lower the temperature, and I could increase the entropy effect and overcome this enthalpy effect to make it spontaneous. So the entropy is what's going to drive spontaneity by making it less than zero, making it negative. If we have an exothermic reaction, then it's real easy for it to be spontaneous because delta H is negative and our positive entropies are going to drive that forward. So that's why combustion is so spontaneous. Once you start it, it's really hard to stop because it's exothermic and you're producing smaller gas molecules. So the entropy of the smaller gas molecules is much higher than the entropy of, say, like a wax molecule, a single molecule with lots of atoms, but it's still just one particle. You break that into 20 particles, the entropy's gone up greatly. So it's not just spontaneous because it gives off heat, which makes it negative delta G. It's spontaneous because of the amazing increase in entropy. So. And then this term for Helmholtz energy and Gibbs energy, we call that exergonic. And so it has buried in it this phrase, this word erg. Have we talked about ergs before? Does that ring a bell? What's the name for the energy unit? Like the SI energy unit, what name do we use? We've been using wave numbers, but it's really not energy. Wave numbers is like the inverse wavelength in centimeters. But like if we were to calculate the energy, so, E equals h c over lambda. And if wave numbers is 1 over lambda in centimeters, it would be h c nu. What is the unit here? What's the energy unit? Joules. Yeah, right, joules. Okay, but we give it the name joule when we're using meters, kilograms, and seconds. So it's a kilogram. What else? Meters squared, good, per second squared. Okay, so that's the unit for energy, a joule. But there's another system of units called the gram centimeter second, CGS. So this is MKS for meter kilogram second. There's also a CGS where you use centimeters, grams, and seconds. So it would be a gram times a centimeter squared per second squared. And that's the energy set of units for the CGS system of units. You ever heard of this CGS system? We're going to come across it in this course a couple of times. And the energy unit for that is called an erg. Okay. So this is and also just the word energy, ENERGY, that erg is right there in the middle. That's the Greek root. Okay. So we see that, and we see also in terms like ergonomics. You've heard of ergonomic chairs and desks and keyboards and all of that stuff. It's an efficient use of energy. That's where that word is. So erg is buried in all of these things. You've been saying that small part of a word whenever you say energy, and so that's when we have this thing that releases energy. We say it's exergonic and therefore spontaneous. What do you think if this was greater than zero? What would we say? Endergonic. Just like endothermic, we just say endergonic. So if I'm going to try to find an open spot here. So if delta G or delta A is greater than zero, we say it's endergonic. Okay, so you might want to write that down. And if it's endergonic, it's not spontaneous. We can really think of, so this, let me just, we can really think of, I'm just putting this on you can put this on the side of your paper. Delta G or delta A, if we want to think of this as really the true hill, then reactions roll downhill, using delta G or delta A, right? That's telling you if it's spontaneous, right? And nature rolls downhill just like a ball on a hill rolls down a hill. There, it's trying to find a lower energy in terms of gravity. Chemicals are the same way, but the hill's height is delta G. And delta G takes into account the heat and the entropy. So it's that combination of heat change, entropy change, that's all rolled into the Helmholtz and the Gibbs energies. And so our true elevation in terms of chemistry is the free energy. Now let's talk about dealing with moles of molecules, and in this case we get to Stirling's approximation. So, you guys have calculators on your tablets or whatever. What's the highest factorial that you run across, like your calculator can do? So to give yours a test. Mine on my phone is pretty darn good. Let's see. My old HP 11C that I got in 1987 can only go to 69 factorial. Okay. So let me see. I think let's do 300 factorial. First, I got to find the exclamation point. There it is. Okay, I could do 300. Let's do 400. Okay, I got to 400. That's 6.4 times 10 to the 868. Wow. 500. Okay, 500 factorial is 1.2 times 10 to the 1,134. Let's see. 600. Okay, 700. Wow, 800. Okay, 900. Wow, I got 900. It's 6.7 times 10 to the 2,269. That's a heck of a power of 10, right? 1,000. Wow, 1,000 is 4 times 10 to the 2,567. Let's see. Oh, I said right here on the screen, my phone can calculate 10,000 factorial, which is 2.8 times 10 raised to the 35,659 power. But that's still not a lot compared to the number of molecules, say, in a mole, right? And when we're doing these statistics, we're trying to calculate all of the possible chairs to sit in, right, with all our different molecules. Those statistics are factorial statistics. And so this is a situation where when we have the number of molecules factorial, we really just have to deal with the powers of those. We have to deal with the natural log of those. And this is Stirling's approximation to get rid of those factorials. So if we had a mole of particles, that's too big to calculate, okay, very easily. We can't calculate it with our computers or our calculators. And so this is where Stirling's approximation comes in. So we could put in Avogadro's number in here. And so if we had if we had a mole of particles, so I put it in for n. I took the natural log here, and that's where the 54 came from. And then I can combine all of those and end up with 3.2 times 10 to the 25th. So that's the natural log of n factorial. Okay. And so that's going to end up being this e to the huge number if we have a mole of particles, and we're going to end up with this double power, right? 10 to the 1.4 times 10 to the 25th. It's absolutely an enormous number, okay? And these factorials are related to that weighting factor. And remember, Boltzmann's equation was that entropy was equal to K ln W. And those weighting factors are all of these n factorials. So in actually trying to calculate the partition function or the entropy of a mole of particles, we need to take some approximations. Also, this weighting factor and also these partition functions are unitless. Now let's look at the Gibbs energy. So as we look at some of the different equations for Gibbs energy, we can see that it's the Helmholtz energy plus PV. This PV can be transferred to nRT. We could break that R into Avogadro's number times Boltzmann's constant. And then we can move that Boltzmann's constant over to the other side and end up with NK. So that PV has become NKT. And then another form of the Helmholtz energy is this minus KT ln Q. And this is a capital Q. So this is what we do when we have an ensemble of particles. So like a mole of identical molecules, like water and so on. So that Q here is equal to the, remember the total partition function is the product of all of the partition functions. And so we did that with water. We had the translation, rotation, and vibrational partition functions multiplied by each other. And then you have the second water molecule. So then all three of those are multiplied by the second one, and the third one, and the fourth one. So it's the same Q multiplied by the number of particles. So same Q multiplied by the next Q, and essentially, you know, if you have two of them, then it's squared. If you have three of them, it's cubed. If you have n of them, then it's to the nth power. So that's where this Q to the nth power came from. Now, we also are dealing with probability, and we don't want to overcount. Those water molecules are not unique. They're indistinguishable. And so that's where we have this divide by the number of particles factorial. So this is what we're doing, the Gibbs energy for, I'll say, an ensemble. For an ensemble of identical particles. And so then we can break this apart, right? We're in the natural log, and so we can take that ratio and make it a difference. So this first piece is negative, so the next piece is going to be positive. So that's where we have the KT ln factorial. And then we have that Stirling's approximation where we can get rid of this factorial piece. Okay. And so that becomes n, the natural log, and minus n. And we have minus nkt, so we have this nkt, and the minus nkt, and then we have the plus nkt. So these guys cancel themselves out, okay? And so then we have nkt in front of the natural log of q, and nkt in front of the natural log of n. Again, that's a difference, so we can go back to making it a fraction. And so we have this setup, the natural log of q over n. We have this nkt in front, and we showed that nkt was essentially equal to nr. And so this part right here is the same as nr. And we can move this n over here as an exponent. So something familiar arises. The number of moles shows up as an exponent. So if you didn't follow the math at all, that's fine. I'm just trying to point out that the number of moles of particles shows up as an exponent of the partition function. So this is the Gibbs energy for an ensemble of a particular molecule type. Now let's put them all together in reactants and products. So you've done this before, the general equilibrium equation, A moles of A plus B moles of B gives C moles of C and D moles of D. So here's our delta G. It's products minus reactants. And so we have those products minus the reactants of the Gibbs energies. So we have the Gibbs energies times the number of moles. Okay. And so we end up with this Gibbs energy equation. And we can move those numbers of moles over here as exponents. So we have minus RT times the natural log of this QC over N raised to the number of moles of molecule C, the number of moles of molecule D, etc. And then we have products minus reactants. And so these minus signs, we're dealing with natural logs. And so we can do a ratio when we get to the natural logs. So this delta G is minus RT, the natural log of all of these pieces, where the products are on top and reactants are on bottom. And we have these exponents of the numbers of moles. Does that look familiar? What does that look like to you? When we have products over reactants. Yeah, so this is the derivation of the equilibrium constant. So this equation we've been using in science, this delta G is minus RT ln K, this is where it came from. It came from this ensemble statistical counting of the molecules in a reaction. It's amazing. And this is a little different than what we've used in our chemistry classes. This is the partition function. And then yet in our chemistry classes, we've been using things like concentrations, right? Or we've been using partial pressures. So those things are approximations to the partition function. So they stand in for it. And when they fail, it's when they fail to represent the partition function. So the partition function is the exact representative of how that molecule behaves. The concentration's a good initial guess, if you will. So for dilute solutions, the concentration works great. You get into really concentrated solutions, it starts to fail to represent the partition function. So we know the exact equilibrium constant. If we could just calculate how our substances behave in solution accurately with the partition function, we would be able to know exactly how every reaction proceeds. So we know all of the math for all chemical reactions, but we can't calculate the partition functions accurately enough. We can for the gas phase. So all of the translation, rotation, and all of that in the gas phase, absolutely. We know those partition functions. But you put that molecule into water or into some solvent, and all of those solvent effects and hydrogen bonding and all of these things, acoustic modes in the solution as opposed to vibrational modes and so on, that really complicates the math. And so we can't do it exactly. So here's our other kinds of simplifications. You can solve for delta G if you know K, or if you know delta G, you can solve for K. So you should be very good at going backwards and forwards with equilibrium constants and delta G. So this is pretty much a miracle. A statistical treatment of quantized states explains the following observations. It explains how heat capacity goes to zero as temperature goes to zero. Okay. It explains that the entropy is a measure of the density of states at a given temperature. So like how much degeneracy you have and how many states you have in a given energy range. That's what we mean by density of states. A spontaneous change, it explains why delta G is driven statistically by entropy. And then chemical equilibrium, that K depends upon the partition functions, and that the equilibrium constant expressions you learned were just approximations of those partition functions. Okay, so our concentration of substance A is roughly, or is an attempt to model the partition function of A. And the partial pressure of A is an attempt to model the partition function of A. Question?
No, that's just upsetting.
It's upsetting? Why? I think it's exciting. What's upsetting? No, I like this. What's upsetting? Why? No, because I mean, how could you explain a partition function to a freshman? You know, no. But we're sort of opening the hood and going, oh, that's how the car runs, you know, right? Yeah, it's the partition function that's driving the car, you know. So, yeah, well, you know more about chemistry than you know about your car, and that's cool. Right? Yeah, so you can say, look, I'm not dumb. I know how the partition function works. Right, exactly. No, it's the way it is. It's the way it is. Everybody has blind spots, right? Yeah. So I don't know the first thing about biochem, you know? And so if someone has a biochem question, it's like, not my office, you know, down the hall, you know? And vice versa. Someone comes down to, you know, Donovan or somebody and asks a PChem question, like, that's down there, go see DW, you know. Chemistry is really varied, even within chemistry, you know, so just some mechanical thing that you're rusty on. But I tell you what, the cool thing about this degree is it's really hard. And so if you can learn this, you can learn anything. Like if you wanted to, like if you're sitting here thinking, I'm not, I'd rather save my money. I'm going to learn how this car works, and I want to, fix this or fix that. You could get on YouTube and you could figure it out. It'd be so easy. Yeah. It's so great. Yeah. Yeah, and then you realize sometimes they engineer the darn thing to where it's impossible for you to do it on your own without special tools. Yeah. Like they put the oil filter on my truck. I mean, changing the oil on a vehicle is so easy theoretically, but you get under there and you see that the oil filter is right above the front axle and suspension, and so there's no way to get that off without dumping oil all over everything else. You have to have a special funnel tray or whatever that would drain that oil over all of that other stuff and get it into the reservoir. Well, I don't have that. And so if I were to do this in my driveway, I would have oil dripping everywhere, all over my suspension, all over me, all over the driveway. So yeah, I can change the oil, but not without some special tools or being able to lift the vehicle up, to where I could get the special funnel in there. And so it's kind of sad. It's, that would save me, $40 or so, and yet it would make more of a mess, and I'd rather not. But it's just a shameful thing. It's like oil changes are so easy, but yeah, sometimes it's not worth the mess. Okay, so on review, we're going to do some big cahoots over this material. We'll look at this spreadsheet version of this. Bring your questions. I really don't want you to not have questions and then Monday disappoint yourself, So, all right.